Hey, thank you so much for having me. I have this tablet that just takes like 5 minutes to open it up. So I'd like to actually see my talk here. Give me a second.
You could just make up the first 5 minutes and then see
Well,
if it still fits.
I have the archive number that I need to get. That's the real problem. Okay, so there's 2, 5, 6, 7, 8. So there's one part of this that's accessible in the real world, and there's another part of this which is actually in here. So we'll see when that can get all typed up and everything. Okay, so yeah, so thank you so much for having me. This has been a really engaging couple weeks. I was just telling somebody else that my brain is now complete, just been tenderized to a nice mush. So we'll see how this all goes. You know, the issue being all the talks have been so interesting. Okay, so I'm going to talk about some TQFTs for derived VOA modules. Yeah, so maybe people in the audience are more algebraically minded, but maybe I'll give the VOA module example just for anybody who's more familiar with those. This is really just a choice of what to emphasize. So yes, so this is this part is joint with Agustina, and this part is just myself. Okay, so all right. So some examples to keep in mind. So I'll say a little bit, and then I'll give a little bit of more of an outline. So let's take, for example, B, your favorite rigid C2 cofinite UA. And then I'm going to be using this category, which I'll denote by A. And in this case, this would just be B module, maybe finite length B modules. And or so I could take, for example, this triplet VOA. Or if you're more of an algebraically minded person, you could take A to B reps small one group, which I've taken to writing like this. But this is maybe just some algebra. You could think with generators, E alpha, F alpha, satisfy some commutator relation, etc. So I'm going to be talking about things like this. So the context being modular, finite modular tensor categories. And so what do we do? So we construct what I'm going to call homotopical TQFTs in dimension 3. Okay, and you can think about these as maybe derived series, or maybe an exotic bulk TQFT, or logarithmic CFT. And so some of the things I'm going to be saying, I'm not being too careful about. Of course, we all understand from Ingo's talks that even this kind of discussion of bulk topological field theory is a bit not suspicious, but there are some details there. But yeah, so right. So from this perspective, maybe I think I'm doing like kind of this kind of construction, maybe like Marco was telling us about, but I maybe want to use some derived category. Whatever. Okay. So what are our kind of motivations? Let's go over here. Our motivations, I would say my motivations, you can ask Agustina her perspectives on things. Here we have these kind of non-semi-simple non-derived. I'm thinking in dimension 3, but dimension 4 is also interesting. Dimension 4 is harder. So we saw derived Bureau theories, and we also saw kind of Rashid drive type theories. And then on some other motivations, so this is some kind of math, and then on the other side, maybe we have some math physics, which is that we want to think about twists of n=4 for supersymmetric QFTs. And if you ask me what a n=4 supersymmetric QFT is, I'll tell you with high confidence that I don't know anything about it. But when you take apparently you take some topological twist of these things, and you get some kind of exotic TQFT. So on the math side, what I'm curious about, which has kind of been avoided to some degree so far, is these kind of miscibility conditions. Let's say miscibility conditions and projectivity constraints. There's a kind of asymmetry in the ways that these things are constructed, where sometimes some projective needs to be some particular place. Practically speaking, one uses maybe a modified trace, but there are constructions. One can construct this 3D TFT, topological field theory that Marco was telling us about, instead by going to 4 dimensions and taking a boundary theory, at which point, if I understand correctly, I will not see the modified trace as long as I want to do this kind of non-compactly. But there's still some kind of projectivity constraint happening there in the ways in which I do something in kind of somewhat, well, anyway, that's there. On this side, the TQFTs you get are exotic, kind of not the things we're used to, not the things we know how to do. So here, maybe I'm interested in, can I construct mathematically a topological field theory, which even looks approximately like the type of field theories which I'm looking at over here. And maybe over here, I'm just asking myself, I'm just confused about these projectivity constraints and miscibility conditions. And then actually, maybe I believe that there's going to be some kind of way of going back and forth here. This is been explained most clearly in the work of Kreutzig, Mafte, Garner, and Gear, so that's not so much, I can't really take credit for any of that. Okay, so what's the outline? So today I want to write up, I want to start just writing up a explicit kind of math conjecture. I'm going to start with the explicit math conjecture. And then I want to think about what I'm saying. Some particular example. And then I want to say a theorem. Theorems. And then I would like to give a little bit of details, more highlights. Okay, so that's the plan. And so I'm perfectly happy if you just yell at me if you have a question. You don't need to wait for me to call upon you. So feel free to interrupt as however you like. Okay. All right, so let's write down this conjecture. This will flow over to the next bit here. So Kreutzig, Demofte, Garner here. Okay, so this is something I'm cobbling together from some stuff said in a paper of Kreutzig, Garner, and Gear. I think maybe the paper was published 24, posted on the archive in 2021, I think. Some stuff that Eddingoff told me when we were eating dinner somewhere. And then just some, whatever is incorrect about this is my own contribution, okay? So, take a finite modular, and we'll do an example in a second. Well, I'll highlight an example in a second. And H connected algebraic group acting on. Okay, and let's A denote the derived category. There should be a bounding here. I'll put it there. And this is the derived. So let me just stop here for a second and tell you something about this, right? So what is this? So this is a category of chain complexes of objects. Okay. But I don't want to distinguish between a given object and its projective, injective resolution. So I'll have my objects of A there if I want to look at them. But if I want to replace them by their injective resolution or their projective resolution, then I can do so, and then I'm doing the same calculation as I would have been doing at the given object. Okay, so this is, Thomas had some example where he resolved some module. I mean, he didn't take a projective resolution. He resolved some module, did a calculation after he did this resolution, did some normalization. So that's the kind of thing that has a flavor like working here. So this is some kind of expansion of the category A itself. And the most important point is that you're actually going to change morphisms. If this is finite modular, I would call this modular in some sense. Maybe my problem is that maybe I need to define the sense.
Yeah. Quasi-isomorphisms.
This is the same as in looking at chain complexes and inverting quasi-isomorphisms. Yeah. There's an important point here there that the bounding would then just not mean that I take bounded complexes, but stuff with bounded cohomology and invert quasi-isomorphisms. Okay, let's let this be this, and then of course H still acts on this. So the proposal is that there exists 3D TQFT. I'm going to write it like this, LRTK. So somehow we decided this should be Lubashenko, Rashotikin, Tarayev. And I should be going from some Poisson category. I'm going to live in this non-compact world because I have to. And this is a slightly different color. And let's do, I want to write this in a scary color. I think it's not quite scary. Maybe I have some kind of 2 here. So I want to have some kind of 3D CQFT, maybe extended, with values in the spaces. And so this is like the derived infinity category vector spaces. So don't worry too much about this. Okay, just I have some kind of homotopical target. This is what I'm talking about, this homotopical there. So just vector spaces, but I make it kind of squiggly. with values here. And I want the circle value. Instead of, Marco said it should be here for him. So for me, I want it to now be derived any category. It should be in pink. So. This is recovering this with the pants giving my multiplication, etc. And this should accept markings. So let's take some marked surface, genus G connected surface. This should be given by the maps in A, linear maps in A, from some power of the cochain to maybe I have markings living at different places. So I need to maybe put them together, multiply them. And so the here's the category, and then the morphism should appear here. This should be some isomorphism with some content that it certainly involves some choices. But it's I would say that you think about this as a representable functor in terms of the labels. That's all I'm saying there. And furthermore, so the entire theory, just a couple to okay, so this extension down is maybe a little bit frightening, and this coupling of local systems is certainly very frightening. And I won't say anything about this, but this is the conjecture that I'll write down here. So let me first look at some particular place where I might want to think about this, and then maybe let me tell you where this conjecture is coming from. But yeah. Mm-hmm.
Are you going to associate to something to a closed surface without any insertions? And will this be a graded vector space? Or?
Yes, so there are a couple questions there. So first, let's say yes, but maybe I could say having this associated to a surface with no markings is the same as marking it by the identity. Okay. There's some content saying that I can literally move the identity, but it would be that value. So I would be looking at these maps with this here, so some higher kind of Hochschild homology. And up to some approximation, you should think about this as Rhom a L tensor G mx, and then up to some more of an approximation, this is really like some kind of X. Actually, I can say this precisely. Maybe the maps. That's Y, 2, so some kind of fancy thing when I look at the cohomology or homotopy groups or whatever that I'm looking at. Okay. So something that, of course, I'm saying that I get some mapping class group actions on these things. I was just talking with Christoph a second ago. When you think about something like that, there's already been literature on the existence of mapping class group actions on these kind of spaces by Christoph and Lucas, as well as a paper that I'm forgetting who was on it. I think Simon was on it. I forget. So sorry. If anybody knows the authors of that one, you can say so. But okay. So let's look at an example where I would maybe think about this. Take A to be representations of the triplet, or triplet models for the triplet algebra. So who is this triplet algebra? It's some kind of extension of the Virasoro at, let's say, 1p central charge. And it sits inside of some lattice, which I forget what exactly the lattice is. Maybe something like the root lattice over some p-scaling of the weight lattice with some form given by the killing form. And this thing admits an action of PSL2. And with the invariance, PSL2 is now going to be equal to the Virasoro algebra is Vira. Okay. So this action of the PSL2, so this is a big algebraic group action. I would never have such a nice algebraic group acting in the semi-simple case. I would only have maybe like a discrete group acting, but here I have this possibility. And so we get a PSL2 action on WP mod as well. So just by restricting representations along that action and in some kind of way, this action should be algebraic. So some algebraic group action on the category. And as I said, so we expect T. Well, I already kind of said this. RT, this homology. This is some kind of, again, up to some approximation, this is some kind of derived conformal blocks for WP obtained by resolving modules. P1, 0, P1. And I would hope that this would have some kind of informal, not completely formal kind of way of thinking about this. But yes, the HOMs, or maybe I think about it as associated with the conformal blocks. So I think that I should maybe have not just the conformal blocks, but I have some kind of derived version of the conformal blocks. And then why do I think that I should have this contribution of flat connections? Well, I don't know exactly why I should have a contribution of flat connections specifically. That's more having to do with, well, something else I'll say in a second. But the deformations of conformal blocks. So I expect some kind of thing deforming this. This should come from the presence families twisted modules along subspaces in this sense. So not only should I be able to take twisted modules for different group elements, but these things should come in families. And I think there's been work of Simon and Fagan on thinking about taking these VOAs with big centers, and these VOAs, I would think about these families of modules as modules over those VOAs with big centers. So yes, so fine. Okay, so this is kind of what this would look like in this setting. And right. So why this particular conjecture? Why this particular form of the conjecture? Okay, let's see. So this particular statement. Okay. One particular statement. Okay. Okay. So I guess I'm just gonna put some names here. Okay, so in the physics literature, Kapustin and Witten tell me that if I take some kind of, I would think about the A twist of this kind of supersymmetric QFT, I should get a topological field theory, which has this kind of flavor. So I'm going to have derived state spaces, and I'm going to be able to deform the state spaces by local systems over the, let's say, surface that I'm putting in here. Gallardo kind of has some additional literature on that, explaining that. So in Korsakoff, Demonte, Garner, Gear, what they say is that, well, if I took it some particular one, and I do this kind of A twist, what I should be getting is a topological field theory for small quantum SL2 or SLN, and that this kind of deformation by flat connections is basically like coming from the existence of the De Contini-Katz quantum group. And their theories, they also associate to these VOAs. And mathematically, we expect this thing, if I restrict to the, take some homology of this recovers at all. And the deformations coming from CFT, TQFT, for the other. And let me say, this derived theory will always have projectives. Objectives. So all admissibility constraints are let's say taken into account or nullified. Okay, anyway, that's a lot of shenanigans. Yeah, so maybe let me take a second here. Okay. Okay, so this is this conjecture.
Can you repeat the last sentence?
So let me erase this, then I'll say something. So this is, who is this? DGGPR. Renzi, Gajudinov, Gear, Runkle, Petru-Morand. I gave them the wrong order, but yeah. So okay, so in this theory, I say that there's some kind of need for there to be a projective present, right? And then also, if I'm understanding correctly, if I want to think about the state space for a surface with a projective versus a surface without a projective, maybe they're a little bit different. So maybe I need to allow this intersecting of red and blue coupons in the absence of a projective, but maybe if I have a projective on my surface, I don't need to allow that, right? So this kind of need for a construction which deviates from the way that I would do this in the semi-simple case. Of course, I'm still going to need to renormalize and think about the modified trace, but in terms of the category that I consider would be kind of, I would avoid that kind of difference, right? Then I can still recover this bit, this theory by taking the cohomology of this one that I construct just using projectives. So it's just something about the nature of the construction of these things. Does it make sense?
What you said, the derived theory will only see projectives. What does it mean?
It means that, well, it doesn't mean anything because I haven't really said anything. But say I can construct this just like I'm deriving a functor, right? I can't really do that, but let's say I can do that. how do I derive a functor? I take a projective resolution of whatever I started with, and then I apply the functor that I'm looking at.
Right.
So all I need to really understand is the behaviors of the functor on projectives. And yeah, and then I took the zeroth homology of whatever derived functor I was looking at, I would recover the thing that I started with for the original object. Yeah. Does that make sense? Okay.
But sorry, but in derived case, you will not need admissibility conditions.
I would say that either they're taken into account or avoided. So this has something to do with like the ways that this is constructed. So I maybe we'll say more about that, but maybe you'll have to, maybe I can maybe explain it later. I mean, that's really a question about like exactly how am I gonna try to do this. Okay.
But you're still non-compact, right?
I'm still non-compact, but I'm non-compact in a much more obvious way because this, even though it's some extremely fancy thing, it still has rigid stuff in it and non-rigid stuff in it.
It has what?
It still has rigid stuff in it and non-rigid stuff in it. This is symmetric monoidal category, let's say, and stuff is dualizable if and only if it has a co-evaluation evaluation. This thing is too big. So I cannot possibly have a theory which closes. Right. So this is another kind of point, which is that if I am thinking about this abelian theory is coming from a derived theory that's actually has infinite state spaces, then there's a reason for me to think that it shouldn't be closing up anyway. Yeah. Okay. Okay. And I should say that for three manifold invariance, the most interesting part would be this deformation, which has to do with this CGP type business. Okay. So some theorems, even though okay, I'm not gonna be able to say anything about that. Okay. A. Somebody did this really fancy D. I've always had problems with D. Somebody resolved this for me during this conference. For this, there does exist non-extended, non-compact, anomalous. Let's say symmetrical functor, so TQFT. LRT, okay. And let me, okay, 42, okay, non-extended, I'm non-compact. And I want to say that I have labels in A, so a marker wrote this slightly differently. And valued in this fancy place with prescribed state spaces. Okay, so without the connections and without extending, at least I can say that this kind of theory does actually exist with these kind of state spaces. I think extending down to a circle is maybe just some formal thing. The more important emission is the flat connections. So let me explain a little bit about what this bordism category is, in part because I'm not completely satisfied with it, and I've been talking with people about making something slightly different. But okay, so I have labels in A. So maybe let me highlight some point here. So in the abelian setting, what would I think about for a this label, this category with labels? So in the abelian setting, I would have, that's not what a surface looks like. Maybe surfaces, maybe points with labels by objects in my category. and I'd have some bordism between this, let's say y1, y2. And then what I would have in the middle, some different color. What I would have in the middle are some graphs. So this is exactly what Ingo talked about. I'm missing my third point. Let's say it's here. Like this. Split. I have a loop around something. Okay, then something happens inside of here, and maybe down here. I split again. Okay, and then these are labeled by F, G. Okay, different morphisms in the category. So this is what I would look like for the Rubin category in the abelian setting with the labels in there. So if you try to label this by some kind of complicated homotypical category, what are you telling me here? Saying take the multiplication of x1 and x3, for example, and map out to some other object and label by this particular morphism. So that kind of specificity is going to be absolutely illegal in this kind of setting where I take this here. There is no multiplication which is actually prescribed precisely. And then when I want to split this thing up here, that's completely illegal. So one needs to do something to the bordism category. This is almost the most important point in trying to move from a abelian setting to a derived setting. So what we're taking at the moment is some kind of easiest case here for labels. Okay, so what? So I believe that there is something much better than you can do than this. But anyway, this is what is there right now, and hopefully I'll soup this up to something more natural later. Okay, so I'll still have some labels here. So surfaces with labels. And here, instead of having a point with a framing, I want to include the entire disk. Okay, so I want to take disks around these. And I actually think about these as embeddings of a disk onto the surface. Okay, so I'm choosing actual coordinates there. And then here, let's draw these slightly larger. And then what I'm going to allow is I'm going to take 2, which I think about as the neighborhood of some ribbon. I didn't draw this right. Yes. And maybe I come up here, and here, and here, and maybe this goes like this. And then, of course, there's some kind of ambient 3-manifold happening here. Okay. So what I would like to do is say that I could actually put like a surface inside of this, but I can't do that at the moment. Okay, and then at the boundaries, here is where I mark by F and some G. So the morphisms kind of only happen; they don't happen inside, but they happen at the boundaries, and that's okay. Okay, so this is going to make sense in any kind of setting. Okay, so. And in terms of the proofs and stuff, it doesn't really matter. Yeah.
So you do not allow saddles inside. So you
like if I wanted to put like these two things merging in the middle and to something like genus 1 or something, or even just merging them, I'm not allowing that. I'm not saying that you can't do that. What you need to do is to write the abelian theory down in a particular way that you can do this. That you can write it depends on how you write the abelian theory, what you can do here. So, let me be very clear about the answer to your question is no, not right now, maybe no, never, but no, not right now. But I think that there is a way to do that where I can allow.
So basically just a braid.
It's just a braid going from one side to the other, but there's something different where here I actually start from the circles and here I end inside of the discs labeled here. And what you should think about this is actually like a pair of pants, which this here, and there's a pair of pants that does that. Yeah. Okay. All right. So fine. And I should say that in here. some non-empty surface must have a label. Okay, so I must have a label. So this is relates to this question about what would I do for an unlabeled thing. Well, at least formally, I'm saying that's illegal. I must have a label. I can label by the unit if I want, but I must have a label. And I interpret this as something about like what Marco was talking about. This I'm doubly non-compact. So somehow I can't have like a surface with nothing.
And the label is from derived category?
Yeah.
Yeah,
Yeah.
I see. Like in the abelian case, I could think about it as a tensor unit.
Yes.
And here you need to resolve it projectively.
Yes.
Right? That's why it cannot be empty.
Well, I would say this. I would say the following. So in the abelian setting, something being one level greater of commutativity up from where you started with is already symmetric. So one, if I put it anywhere, I can literally remove it. It literally doesn't change anything at all. But here, if I spin around one and I try to evaluate that, there's some kind of way of removing the one. There's some way of putting one across somebody else, and there's something happening there. Basically, the subcategory generated by the unit is going to be like E3 instead of E infinity. And so I can't just like do whatever I want with it. Okay, so there's that. And then, okay, I think I started at 11:40. So, okay, so there's that. And that's, it is what it is, I suppose. Obviously, if I wanted to think about doing some conformal field theory with this, I would, maybe I think I can do something with this, but I definitely want to do more. But yeah, this can, I would almost assert this can be improved to something much more natural, which I still know how to do it. Okay, so the second theorem, that after homotopy truncation, in the target, I can remove all labels. So now this is going to go from an unlabeled just 4 through 2. And now I'm going to what's called the homotopy category of this, but what is this? This is just the discrete, so the kind of triangulated derived category. Okay, so as I said, we're working in this kind of homotopical setting. Everything's squiggly. Everything can kind of move around. There's homotopies and stuff like that. But if I just truncate and I say that there's nothing interesting happening in some higher levels, and I force this to be a category, I'm going to get the usual derived category. So write this like maybe a Roman kind of. So if I do that, then I can just remove the ones for precisely that kind of the reason that I said. Now E3 collapses to E infinity, and I can really remove everything. And so the values of this are going to be that is R. Maybe let's put a star here. G. Whatever. Okay, so what's going to happen here? So what's the distinction between these two different places? Okay, so let's look at this. Let's look. So now, sigma G. This accepts a strict action. By whatever, by the mapping class group, okay? So these things living inside of here accept a strict action by the mapping class group. This thing oh, sorry, there's no label here. This is just one. This thing, so I think about a one is living somewhere as an action of some infinity group sigma. And inside of here is basically a pi one. Okay, so pi one accounts for the fact that I need to have this tube going from one side to the other. It's not exactly pi one, but it's almost pi one. So I'm essentially, I can act at a homotopical level, but I need to act by this kind of extension of the mapping class group where I include the fundamental group, just because I need to think about going from one side to the other. I cross this in the kind of, if this was the identity, that would just be something like the fundamental group. And maybe this is even something more interesting. So
strict action is still projective for different reasons.
yeah, I just mean that I don't have this kind of squiggly stuff happening. Yeah. So yeah, so the comment here, which maybe has to do with what maybe going to address a little bit more what you're saying. So Schweigert and Woike, so they say that, okay, they were just looking at the mapping class, sorry, they're just looking at the modular functor. So they say that there's actually, if I take the same setting we're in, take some modular tensor category, look at the derived and infinity category thing of it, maybe they don't say exactly that, but they're basically looking at the, where am I? Oh, I'm here. They're basically looking at something like the two-dimensional slice of this, maybe with a little bit of down a little bit, and then they just include the mapping class group stuff. And so then they're saying that actually at this level, basically, I can obtain a strict action of the mapping class group. So I don't have to have labels for them. So they're getting something, I'm getting something more complicated than they're getting, but when I do this truncation, I'm getting something which has less information than they have, but whatever. So presumably this extension actually, this action of this extension actually factors through this quotient, but that's not, I don't have the knowledge needed to say that. So that's one point. The second point is that if I think about stuff beyond the mapping class group, I think I actually do need some decorations here for reasons that maybe I won't get into. It has to do with what the circle value actually is. It can't be like, there's certain things that it can't, properties that it can't have. So I think this phenomenon of this collapsing of this extension is maybe specific to this setting here. Okay, so let's see what kind of time I have. Yes.
The thing with the tilde, this is the mapping class group of sigma with one function, right? This is what you're saying.
This is the automorphism group of sigma in my category.
Yes, but this happens. I mean, this isn't that. So this should be the Birman sequence, right? Is that the?
Yeah. I mean, I think if you include a puncture, yes, this is what you should.
So then, but then if you insert the unit,
yeah,
somehow some of this extension term that you have the pi one, this shouldn't it follow from the TQFT principle that this extension term lies in the kernel and that then it descends?
Well, I mean, like I said, this is the automorphism group of this thing in this category, which I constructed in some particular way.
Okay.
Right. So there's no general principle that I think would tell me.
Well, the thing was constructed for the markings, and then you're replacing these markings with the trivial one. And then what happens in this approach of Lendler, Sommerhauser, and Schweigert is that somehow they show that this extension term of the Birman sequence lies in the kernel, at least on the level of cohomology. It really lies literally in the
level of cohomology. I've already got that, right?
Yes, okay.
I mean, this is even better than cohomology.
Yes, yeah. I mean, yeah, this was this refinement that we did, but I think it should still be true.
No, this is less than the refinement that you did. The refinement you did is up here, I think. You operated
I
at
see.
cochains,
Yes.
right? And cochains maps to this fancy thing. So if you can resolve this problem at the level of cochains, you're resolving it at this squiggly level.
Okay, but the thing that you're pointing at right now, you're saying that here it's not clear that the pi1 lies in the kernel.
It's not clear, but I'm also not an expert in this stuff, right? So,
Okay.
I mean, maybe if an expert like yourself, looks at it, then maybe you can conclude this, right? But all I'm literally saying is, what's the automorphism group of this that acts? It has like a pi1 in it.
Okay.
Yeah. Any other thoughts?
This bordism category is non-compact or it's
Yeah, non-compact.
no here.
Oh, sorry, yes.
Okay.
I again have the same problem with infinite dimensional state spaces. So.
In your first theorem, is it an infinity functor or is it a functor? I'm a bit confused.
Once I'm in an infinity world, I don't even know what these are, so I'm using.
So which are honest one categories and which are infinity categories?
This is an infinity category.
Okay.
So maybe I can explain a little bit more. This is an infinity category, this is an infinity category, this is a symmetrical monoidal infinity category, this is a symmetrical monoidal infinity category. This is a symmetrical monoidal functor between infinity categories. Why is this an infinity category? For one, because at the boundary, if I take the fiber, this thing forgets down to something with labels by the trivial, just like star, just 1 point category. What are the fibers of that over a marked surface? It's just a product of the category, the infinity category I started with. So this has to have some infinityness because of it. I'm living at the boundary. The second point is that in DGGPR, they say that, well, this theory is kind of invariant under scaling relations on this thing. So the way that you can put that into here is to say that this is actually allowed to move. So I also have a mapping space involved in the map and in the mapping spaces for this category as well. So this is infinity in a topological sense and in an algebraic sense. And you get to choose how to construct this, and it's a non-trivial thing. And there may be different choices and stuff. Okay. Okay. I was going to say something about that. Okay. Let me say maybe something. Okay, so what did I want to say? Yeah. Okay. Well, that's gone forever. Okay.
About admissibility conditions, like this, or do you have some objectivity stuff inside? Or?
Stability conditions. Well, there are. First of all, I mean, like the construction is kind of opaque. So
The such as what?
kind of opaque, right? But again, I literally, so I'm going to say a little bit about how you construct this. I probably won't get to this point. You construct this by taking, you start with a chain value theory, and I'm going to say this again in a second. You start with a cochain value theory. You say that cochain value theory somehow respects algebraic homotopies between the two, the source and the target. And then you say, okay, I can localize this with respect to those kind of homotopies, and that gives me a theory with labels in the homotopy infinity category. And then I can con-extend to the derived category, to labels in the derived category. When you con-extend, you don't actually know what you did. But what you can do is say that, well, I expect this con-extension to be calculated by resolving projectively in the place that I started. So in principle, what this does is this is taking something for the cochain value theory, projectively resolving for you, and then taking those values, but then I do it in with such a machine that I resolve every single problem that could have occurred when I did such a thing. And so what this is just looking at the projective part, it's just looking at the abelian theory with projective labels. It just looks at that. So it is, and I'm saying I'm not allowing an absence of labels, so everything already has a projective label. That's the part of the abelian theory that I'm using. Oh, I should also say, and another thing is that and then you can recover the abelian one from this one, which only uses the projectives by taking the zeroth homology. So yeah. Okay, so So maybe I'll say a few words about how this. Well, I've already erased half of this, but any more questions before I erase the other?
You didn't explain this hard symbol, I guess.
So this hard symbol means that inside of this bordism category, which I have most of it here. So any kind of subcategory inside of A, or if I have a map of stuff from something to A, I'm going to be able to restrict this theory to that. So this thing has a T structure, and the heart of it is this. So I'm saying restrict to the heart, and then look at that. And then the point is that when I do that, I'm actually going to land in a certain place where I can take homology, and that's actually going to be a modal functor. In general, taking homology is not a monodal functor. So after I restrict to this, so that I can take homology, it's monoidal, then I get this thing.
So this LRTA is just.
This is just Dorenzi. This is your.
Okay,
This is your thing. Yeah. Yeah. Okay, anything else? Okay. So let me. Okay, so I'm sure this is all very frightening. So let me just highlight one important point of this construction. Of course, I can't go through the whole thing, but how does this happen? So the first point is that construct an extension of this DGGPR theory from the abelian category to a theory for maybe there's some admissibility condition here, and here I take chains in A. I'm going to write this 1,000 times, but it's always with the bounding. And since I'm taking the bigger one where I allow all this kind of fancy stuff to happen here. It's exactly the same kind of bordism category that they have in this original paper. And now I map to change the vector spaces, in which respects. Okay, so if you look at the surface with labels by some certain cochains, what you're going to get is the cochain harms, which are the inner harms from the action of chains of vector spaces on this category. So another way to think about this is basically modular, but it has mu center equal to this. So I'm getting a topological theory which values in the mu center, which is maybe a natural thing to think would happen. Now in here. And so what I mean by respects homotopies, so if I take some surface, I cross with the identity, and I just take straight lines, well, these are all homotopy equivalences. This is going to map to a homotopy equivalence of cochains. So this is kind of the starting point. So now, there's some symmetric monodal functor. So now, so I can localize this back to homotopy equivalence to get a symmetric monodal functor. Compact 32 chains H top. And so this is going to go to chains vect. And this is going to be symmetric monodal. That's going to come along for the ride. And this is already the infinity category of GG vector spaces by some well-known but very hard calculation that happens in someplace, higher algebra. This is gobbledygook. I don't know how to spell that. This, you have no idea what happens. If you localize a general category, you're not going to have any control over what actually comes out at all, okay? So I can say this occurs, I can say this is some fancy infinity category of stuff with labels somewhere, but I actually have no idea what this looks like. And so what you need to do is put myself in an advantageous setting for some generic operations. Generic operations. So what this, what I need, so let's instead take this subcategory of stuff like I had on the board. Okay. I'm not going to say too much here, but let me just say a few words. So let's restrict instead to this bigger bordism category. This thing gets down to 2. And this forgetful functor is actually a co-Cartesian, it's called a co-Cartesian fibration. It's co-Cartesian fibration of special modal infinity categories. And it fits over some map to some operad. And this is now tensor, and then this is now pullback. Okay, so what this forgetful functor is intersecting with the outgoing boundary. Okay, and this is basically some kind of framed color D2 operad. And so when I intersect with the boundary, I erased my picture, but what was happening at the boundary was I had some disks, and then I had other disks living in them. And so if I just remember these disks and these other disks living in them, I'm here. The category of chains is algebra over this operad, which means that I'm a co-Cartesian fibration over this. And when I pull back, I get this category here. So this is now a co-Cartesian fibration. So, and the point is that this, and now I can do stuff for this. This, you know what happens. Okay, so what you do is now when I localize this, first of all, this makes sense to talk about this category in any setting. Take any fibration over a frame D2 operad, and that's going to be basically a ribbon tensor category. So take any ribbon tensor category, infinity category, pull back along this map. That's going to give me my label category here. I can localize this. It will be the same as localizing this, which is changing, for example, chains to homotopies, etc. So from this, I can define. From this, I define. And so this is the last thing maybe that I'll write. Again, I realize this is not people's wheelhouse, but I do want to say it. You can keep it in your mind later. Fine. Let's go back. So now it makes sense, and now I can kind of do things. So my point that I want to highlight is that when I think about a category with labels, what I would like to always do, and I think this is like something that actually can be an important point, is I would like to always say that a category with labels and some bordism category with labels and some other categories should be a co-Cartesian fibration over the one with trivial labels. And so, for example, I could have a bordism category for getting the cob or whatever. Okay. But yeah, so once you do that, then you can kind of start cranking some machine. Okay, so let me not go into all the details. Let me just say that from now, here on, you localize the spectral homotopy. You'll get a TQFT for this labeled by the homotopy infinity category. And then again, you kind of conics and try to analyze what you get. Okay, I'm over time. Let me stop there. Thanks a lot. Yes.
Thanks a lot for this very nice talk. We have time for questions.
Yeah.
So ribbon tensor infinity, is that a thing?
I don't know that it's a thing. So what is this? So this is two. There's a red framed operad or E2 operad. There's a blue E2 operad. Over the red one lives your category. Over the blue one lives the opposite category. And there's a red-blue interface. The interface I label by the duality, and I have these twisting on both sides. So what that's going to be is say that I have a braided tensor category, its opposite category, and I require that the with a twist. This one has a twist, and I require that the duality functor is an equivalence of braided tensor categories with a twist. Now, in making this operad, I don't demand that you actually are A op in this interface's duality. It could be A, B in some interface, which is just something which preserves the. So basically what I'm saying is that if I have a tensor category, it should be this, but maybe there's a more refined thing that actually precisely captures the breaking. Yeah.
Did you do, or can one do some calculations of topological invariance?
Like three manifold invariance.
Yeah, like three-manifold invariance. So is this category or one of these, does it contain like say closed manifolds?
Well, no, but as we were told before, you can just scoop out a ball, right?
Again?
You can just scoop out a ball, take a closed three-manifold, scoop out a ball, and the way that I'm kind of oriented, I will get a number out of that. And so you can look at what you're going to get. Now you'll note that that will only. When I look at the empty thing, that's basically going to go to the complex numbers. I have a map to this very fancy place, but it only knows about what's living in degree 0. So I'm mapping from something in degree 0. So actually what I'm going to get out is some invariant for the abelian one. And what you're going to get out is the, I forget I calculated at some point, but it's one of these invariants maybe by labeling by a projective and putting a circle, P1 and putting a circle.
Yeah, right.
I think for three manifold invariants, one of the things that I would like to do is to set up some machine, study this extensively, and then maybe have some Rustic and triumph theory for more complicated infinity categories that don't have what's called a T structure. In which case, you do have the possibility of obtaining more interesting invariants, and then also the connections is the more important part for invariants. So just from this three manifold invariants, I would say this is not where you want to.
You get the same, basically, you get the same invariance.
You get the same
in
invariance.
case.
This is not going to tell you anything new in terms of three manifold invariants.
Okay.
Coming to Azad's question, is there any chance to get invariants which take values in the derived form from the monoidal unit to itself?
Yeah, you will get that. What I'm saying is that in degree 0 is just the standard hall.
Yes.
And that's just C.
Yes. And what about higher degrees?
Maybe there's some way to cook that up, but you would need to change the morphisms in your target category. So still, what the higher degrees do is have to do with homotopies between morphisms. So here's a morphism is here, and a homotopy between them, I go up here, and then I go up there. And so, the map itself does not include this stuff here. So what I was saying before is I think what you want is you want some input category that has interesting stuff in degree 0 and kind of goes maybe in both directions when I take the extensions of the unit. And then I might get some interesting three-manifold invariants. But of course, I can't claim that I can do anything such as that. But that's part of like,
Okay. The
Yeah.
future.
yeah.
Okay, if there are no more immediate questions before thanking Cris again, let me say that today lunch is in the university restaurant, so please pick a ticket here if you want to go to lunch. But let's thank Cris, and let's also thank Marco.
Oh, very good to see you.